Everyone, Mr. Andrew here. Today, I wanted to look at some of the different kinds of calculations that you can do revolving acids, their concentrations, their pH, and their pOH. Okay? So, to help illustrate this, I pulled a question from one of our worksheets. It says, consider a 0.00475 molar solution of HNO3. This is nitric acid. And I want to be able to calculate the pH, the pOH, the concentration of hydrogen ions in molarity. That's what these brackets mean. They mean the concentration in molarity, and the concentration of hydroxide ions in molarity. Okay. Now, the good news is there's a few ways to go about this. Okay. So we're going to look at some different ways that we can do this. Okay. The first thing we need to do is we need to identify is um, the solute that we've been given an acid or a base. Now, generally, we write formulas of acids and bases in a way to kind of clue each other in on what kind of substance this is. For many common acids, you will see it written with a hydrogen, an H, in the front. So some common acids would be like HNO3, HCl, H2SO4, things like that. You'll notice that each of these has a hydrogen or hydrogens, in H2SO4's case, in front. These indicate that these are hydrogens that will be lost when added to water. These are what are called acidic hydrogens. Okay. Now, conversely, bases are commonly written with a hydroxide at the end, one of these OH groups. So you might see, for instance, NaOH, CaOH2, things like this. Okay, generally you got hydroxides at the end. Okay, there's a bunch of examples, but they're escaping me right at this moment. So acids have hydrogens in the front. These are acids. And bases have hydroxides at the end. Okay, so our substance, HNO3, is an acid. And what that means is when you put this in water, it's going to lose its hydrogen. It's going to donate it. Okay? So the first thing that we want to do is we want to switch this conversion or this concentration from the concentration of HNO3, our acid, to just the concentration of hydrogen. Okay? And to do this, the most simplistic way to look at it is you're going to multiply the concentration of the acid by the subscript of hydrogen. That's the number that comes right after the H. So for this one, because hydrogen does not have a subscript, its subscript is just 1. If, for instance, we were looking at like H2SO4 right here, its hydrogen subscript is 2. Okay? So our concentration of hydrogen in molarity is going to be equal to 0.00475 molar times just 1, the subscript of hydrogen, which makes it 0.00475 molar. Okay, so I'm going to put this answer next to C. Okay, 0.00475 molar. Okay. Now, from here, there's a bunch of different ways we can take this. Okay, but it really depends on which formulas we know and which ones we're most comfortable using. Okay. The most straightforward way is to take this concentration and convert it to pH. And that's because pH is equal to the negative log of the concentration of hydrogen ions specifically. Okay. Now, if you're not familiar with logs, don't worry. It's just a different kind of mathematical function. Okay. So I'm going to pull up my calculator. Okay. I'm going to clear it off. I'm going to take the negative log. It's important that you do the negative log of 0.00475. And what I get is 2.32. So pH is equal to the negative log 0.00475, which is 2.32. This is my pH. Okay. From here, I can really quickly get my pOH because pH plus pOH is equal to 14. But I've already got my pH right here, so I'm just going to plug it in. 2.32 plus pOH equals 14. If I subtract 2.32 from both sides, I'm using my algebra skills here. It's going to cancel, and I'm going to get 11.68. Okay, this is my pOH. So my pOH is 11.68. Lastly, I need my hydroxide ion concentration. Now, here's the thing. pH and pOH are similarly related to hydrogen and hydroxide. And let me explain. I already told you that the pH is equal to the negative log of hydrogen ions. Well, the pOH is basically the same thing, but for hydroxide ions. pOH is equal to the negative log of the concentration of hydroxide in the solution. Okay. So the math operation is the same. It's just what concentration you're dealing with that's changing. So similarly, we can go in the opposite direction. Okay. The concentration of hydrogen is equal to 10 with an exponent of your negative pH. So to use my example right here, my pH is 2.32. So if I did 10 to the negative 2.32 power, I would get my concentration of hydrogen, 0.00475. Okay. So similarly, my concentration of OH minus is equal to 10 to the negative pOH. And because I have my pOH right here, my concentration of OH minus is going to be equal to 10 to the negative 11.68 power. So let's plug that into my calculator. And my answer is 2.09 times 10 to the negative, I believe it was 11, let me double check, negative 12. And this concentration is in molarity. All of these concentrations for these are in molarity. So my answer is 2.09 times 10 to the negative 12 molar. Okay. So here are some formulas that you should remember. Okay, these four, as well as one that we used earlier, pH plus pOH is equal to 14. There's one more that you can use that is pretty common that saves you some time. That is the concentration of hydrogen times the concentration of hydroxide is equal to 1 times 10 to the negative 14 power. This one is useful. It helps you save some time, but you can get by without it. But you for sure should know this one, this one, this one, this one, and this one. If you know those 5, you should be able to navigate between any of these problems. You should be able to go from pH to pOH to concentration of hydrogen to concentration of hydroxide basically freely. Okay? So, that being said, for review, make sure that you remember these formulas and make sure that you can apply them.